Hey, good morning, everyone. I think we'll wait maybe one more minute. We've got, I know we have some large numbers that are attending, and I see a lot of people joining. We'll give it 1 minute and then we'll get started. Thanks. All right, let's get started. Good afternoon to everyone. I appreciate everybody joining us today. My name is Greg Johnson. I'm the GM for FluidTech for the America Sales Group. I'm coming to you from my home office in Houston, Texas. On behalf of FluidTech and all of our channel partners around the globe, we'd like to welcome each of you and thank you for attending this seminar on solving oil breakdown issues for hydraulic systems. We hope that everyone is staying healthy and safe and thinking about and praying for those that are affected by this pandemic that's crossing the globe. Over the next few months, FluidTech will continue to host a series of webinars that focus on different lubrication topics. I encourage everyone to take a look at our new website, which, by the way, was launched today. We'll be posting all of our new upcoming webinars as they're scheduled. Due to the nature of FluidTech's business, we have been designated as an essential business, and our products and services will remain available over the course of this pandemic. Our sales group and distributors have understandably slowed unnecessary travel, but remain fully available by telephone. Having said that, please feel free to contact any of us, distributors or direct FluidTech folks, if you have any projects or questions that you'd like us to get involved with. And although I doubt that any of our operational folks are on this call, I would like to recognize them for accomplishing a record month for FluidTech in March. Pretty outstanding considering the environment that we're all working in right now. Today, we're going to keep this call to an hour. We've muted everybody on the call, but everybody has the ability to ask a question or make a comment if you're following the presentation online. We'll reserve the last 15 minutes of the call to address as many questions as possible. We're anticipating over 200 participants on this call. I think we had 170 or so that have signed up for it, so I would imagine some more will be joining us as the session goes on. I know Greg is anxious to get started, so for those of you that are not familiar with Greg Livingston, Greg is FluidTech's Chief Innovation Officer. For over two decades, Greg's been involved in recognized as a leading authority in contamination control and condition monitoring for lubricants. He's a certified lubrication specialist and serves in official capacity for many lubrication councils and panels, including ASTM and STLE. He has over 40 papers published across a wide range of industry-leading publications. He has been involved in really too many to account, lubrication-related counseling projects, and the list goes on. So without further ado, I'll hand it over to you, Greg.
Wonderful. Thank you, Greg. So we made it easy for you. If you just remember the name Greg, you got both of us here. So, and again, just to reiterate what Greg said, our hearts and thoughts really go out to not only all of you here on the call, but also all the people on the front lines in the healthcare industry that are working on this. And there is no question. I think this is going to have this event's going to have a profound impact on us. And so during this time, us from FluidTech, we just want to wish you and your families a safe, healthy time and wish you all the best. So on a lighter note, I will go over to the presentation here and turn this off so you don't have to see me the whole time. Here we go. On a lighter note, as Greg said, it is our 25th anniversary this year, and today in particular is a special day because we are actually launching a new branding. So I'll just give you a little trailer video here of just kind of showing the, at least on the logo, what we have done. All right. So Josh, who leads our marketing team, he's been pulling all-nighters and putting a lot of effort in with his team to create not only a new website, but over 1,000 different documents have had to be upgraded. And so we're excited for this new kind of branding image. And for me, this is the first time I get to use this new PowerPoint template as well. So getting to our topic of the day here, we're going to discuss what is oil breakdown, specifically in hydraulic oil systems. Why do we really care about this? What can we do to measure? And how can we control this? All right. So what is hydraulic oil breakdown? It's basically when you have a chemical or physical change in the fluid that starts to adversely impact the performance. And often the result of these chemical or physical changes in the fluid forms deposits or this substance known as varnish. So what do we actually mean by varnish? Well, varnish is actually just kind of a generic term. And there are literally dozens of different chemicals that will make up a varnish deposit. So it is based on the operating conditions of the machine, formulation of the oil, and all sorts of various different contaminants that may ingress into the fluid that can create unique new oil degradation pathways. So we just define varnish in a very simple way by saying it's an oil-derived deposit. These deposits come in a wide range of different appearances. So they can be a gelatinous in nature, or gooey, or stretchy, or sticky, or powdery. So we see it come in a wide range of different consistencies, and not quite a rainbow of colors, but many different colors as well. So we've seen some really bright colors to some very dark black, grayish colors, and almost everything in between. But ultimately, what we are, there's various different modes of degradation that are causing this fluid to break down. If you happen to see my colleague Yo's webinar last week, he showed this slide, and he was talking a little more on compressor fluids and journal bearing challenges, and focused on gas and incompatibility as a couple modes of failure. So I'm going to just talk about oxidation and microdieseling. And again, going through this in detail is probably beyond the scope of this webinar, but the big point I want you to take away from this is that there are, in fact, multiple different modes of degradation that are that can be occurring and causing the fluid to break down. So the first one is oxidation, and this is intuitively something I think we all understand. And using an apple as an analogy makes it pretty easy. And we use this analogy for two reasons, because everybody knows when you take a bite of an apple, what will happen if you leave it exposed in your room for a period of time. It's going to start to oxidize almost while you're watching it. But we also like using the analogy of the skin of the apple is akin to antioxidants, say, that may be in your fluid. It makes up a very small percentage of the overall volume of either the apple or the oil. But as soon as that little protective layer is removed, then the apple, or in the case of the oil, will fail rapidly. So what is actually happening here is that when oxidation occurs, essentially this is just the formation of, it's corrupting a molecule and forming an unpaired electron. And basically this unpaired electron, this molecule is not very comfortable having an unpaired electron. So it's looking to grab another electron from something, and it will grab another electron from a healthy molecule, and it triggers this chain reaction. And it will continue to go on and on and on in a process that we call autooxidation. And it will go on and on and on until all of the healthy molecules have been corrupted, and or there's something that terminates that. And so what actually terminates this auto-oxidative reaction are antioxidants. And so there's a couple different types of antioxidants. You can have primary antioxidants, which they'll either accept the electron or donate an electron to the molecule, or you'll have a secondary antioxidant, which will actually decompose one of the oxidative degradation products known as peroxides. So the thing to keep in mind here is that once oxidation happens, if you don't have any oxidants in your fluid, this is a reaction that will continue to go on and go on and go on until everything fails. So hopefully, if you have extreme levels of oxidation, one thing that may occur is you'll see the viscosity increase, and hopefully you've never seen an ISO 32 oil have a viscosity increase like this. This is an incredibly extreme example, but it is possible for oxidation to cause viscosity increases. I would say it's not so common, especially in newer formulations. In older formulations, say using a group 1 base stock with a little higher solubility, it keeps all of these degradation products in solution. So some of these degradative products will have a higher chain length, higher hydrocarbon chain length, higher molecular weight, and will therefore impact the viscosity of the fluid, whereas more hydro-treated, highly refined base stock, like a group 2 or a group 3 base stock, these degradation products are really not so stable in the fluid and will come out and form deposits. And so in most, say, group 2, group 3 formulations, you don't actually see viscosity as an impact of oxidation nearly to the same level that we did, a decade or two ago. So the second mode of degradation, which really is specifically ties to hydraulic applications, is a process called microdieseling. And so microdieseling is a phenomenon that now we've moved to from the kind of the slow, gentle degradation of the fluid from an oxidative perspective to a much more rapid event-based degradation, dealing with really high temperatures that we would categorize as thermal degradation. And thermal degradation essentially is when you have a high enough temperature that can actually crack the backbone of the hydrocarbon base stock, and typically we're seeing events that will cause these really, really high temperature zones in the fluid. And in the case of microdieseling, this occurs when you have air bubbles that are migrated from a low pressure zone to a high pressure zone. The air bubble will collapse upon itself, essentially producing a submicron carbonaceous particle. This particle is it's unique. It doesn't have a high level of solubility, so it's not really going to go into solution of the oil, and it's going to be suspended in the oil in the submicron form until there's enough of these particles that generate that the fluid will become black in color. You may have a patch that looks like a piece of the midnight sky, extremely black. But basically, if you have hydraulic oil that starts to look like engine oil, this is something you may want to investigate. And so one of the primary places that we see this is in phosphate ester electrohydraulic control systems for steam turbines. There's some hydroelectric hydraulic systems and in the governor system that may have microdieseling. Sometimes we see these in compressors, but microdieseling is very much an application-based degradation mechanism. For example, we've never seen this in, say, a gas turbine or a steam turbine. So it's very much application specific, and it's especially susceptible to hydraulic systems. So just keep that in mind. Your fluid starts to turn black, you may have microdieseling, and then there's specific things you can do to kind of to correct that problem. And just a little public service announcement that social distancing is something that we are all practicing right now. This is actually not too bad for your oil as well. So just along the lines of compatibility, oils don't mix so well. Practice social distancing on your lubricants as well. All right, so that's just a little bit about oil breakdown. Why do we care? Well, essentially, oil breakdown is impacting and impairing the performance of the lubricant, which ultimately relates to your operation and the profitability of your operation. So, but some of the impacts that we see with formation, valve stiction is a big one. And so as a servo valve is moving, there's extremely tight tolerances. And so just a small buildup of deposits can really impair the functionality of the valve, may cause the valve to stick, or in some cases seize, and your system's not going to operate or be controlled so well if your servo valves aren't properly being exercised. This is a picture from a plastic injection molding machine, also a fairly heavily varnished valve. Varnish can also coat filters, causing filters to kind of slime over and shorten their life. If you have deposits on gears, it can cause varnish can kind of attract other dirt, debris, wear metal type material and create a sandpaper-like surface and actually increase the wear rate in gears. And heat exchangers is a fantastic place for varnish to form. Unfortunately, varnish has one of its properties is that it's a great insulator, and so you have a plugged heat exchanger or coated heat exchanger with deposits, it's not going to function so well, and therefore it's not going to allow you to maintain the temperature of your oil. And then finally, in hydraulic systems, we see pumps are also impacted by deposits, and so we see premature pump failure as well. Okay, so we're going to do a quick poll here, and because I'd like you to see what is the biggest management problem that we see with hydraulic oils, and love to get your thoughts on this. So let's go over to Greg. Can you run the poll here for us?
All right, I will open it up right now.
Okay. What is the number one biggest management issue with hydraulic oil? The correct oil analysis tests are not performed. Incompatibility or incompatible fluids are mixed together, resulting in deposits. Cheap oil is purchased, and people are basically buying cheap oil, and that fails rapidly. Or poor storage practices. Let's see. Show results. Let's see. Does this give you an opportunity to select one of these 4 options? Well,
I don't see where it gives a opportunity to poll. We'll work on it. Just continue on. We'll work on this.
Okay. All right. That sounds good. Okay. Excellent. Well, I want to make the argument here that in fact all of the different answers can all be certainly challenges, and if people are buying the cheapest oil possible, that's certainly a challenge. If you're not storing the oil properly, that's a pretty major challenge. But I really believe the biggest management problem that we're seeing with hydraulic oils right now is on the oil analysis side. So one of the business philosophers or strategists that I really like is Edward Deming. So he has the saying, you can't manage what you don't measure. This is a principle we hold dearly at Fluid Tech. I think pretty much everything we do, there's metrics around it and we measure. But from an oil analysis point of view, this is why we're doing oil analysis. And if you are not running the right tests that are identifying how the oil is failing and how it's breaking down, well, then you're going to run into problems. So this really, I think, in the world of hydraulic oils is the biggest management issue I think that we have. So let's talk a little bit about how we go ahead and measure these fluids. So some of the key tests for monitoring hydraulic oils, viscosity. You want to look at contaminants, interaction with contaminants, chemical changes, and oil degradation. And so ultimately, when you select your test slate for oil analysis, the first thing you need to understand are what are the modes of failure and what things should I see that will change over the life of the fluid, and how does that directly tie to the performance of my equipment and the performance of my fluid. Viscosity is something that does not change so much, but why do we put this here? Viscosity is really the most important property of the fluid. And even though viscosity may not change due to oil degradation, if you, at least under the vast majority of circumstances, if you inadvertently add a different grade of fluid to your system, that will change the viscosity. Therefore, it really is, it's an important property and should be something that's involved in any oil analysis program. Contaminants, I would say in the world of hydraulics, this is something hydraulic oil users are really on the cutting edge of. And understanding particle counts and water, really, really critical. Interaction with contaminants. So what happens, how does a fluid interact when you have a bunch of water mixed into it? How quickly does it separate from water? Or air bubbles. Do the air bubbles form at the surface and create foam? Do the air bubbles dissipate quickly when they are formed or contained inside the fluid? So these are all important properties to manage. And then oil degradation certainly as well, because it is one of the primary modes of this fluid failing. So we should be understanding oil degradation. So monitoring hydraulic oil failure, contamination, I guess we understand this. We're not going to go into detail on hydraulic oil test slates for measuring contaminants, but the contaminants that we want to measure are basically, if you think about us humans on this earth, we have land, we have ocean, and we have air. These are the things that we also want to measure in the oil. So how much dirt do we have in this oil? This is the dirty totes. This one apparently is full. But you can see extremely dirty atmosphere for this hydraulic oil, water and air. So all critical properties that we want to monitor. The next is oil degradation. And so oil degradation, again, I would say this is really one of the biggest problems that we see with hydraulic oils. Most hydraulic oil users are running oil analysis. However, traditional oil analysis package does not do a very good job of identifying varnish problems. So viscosity, acid number, metal spectroscopy, water particle counts. In most cases, these cannot tell you if you have a varnish problem. However, we have a really, really simple, good tool for this, known as memory and patch color imagery test. And the ASTM D7843 is the test procedure for this. This was developed for turbine oils, and starting in the early 2000s, really to address this this varnish pandemic that was impacting gas turbines. And again, in the world of gas turbines, all of these gas turbine failures and unit trips were happening, and all of the oil analysis results said everything looked good. So we had to develop a test specifically to look for varnish formation. The MPC test is it's a simple test. You add a little bit of oil with a little bit of solvent, and you filter it through a membrane. The membrane is 0.45 microns. Basically, if the color of the patch is dark, there's a high chance that you have varnish. If the color of the patch is light, it's suggesting that you may not. So it's a simple test. We use this little color photospectrometer here to actually measure and quantify the color on this patch. But one thing to keep in mind, a lot of people see this and they intuitively think, well, okay, if my oil is dark, I probably have a varnish problem. And there should be a correlation between the color of the oil and the patch. So it's a little bit counterintuitive to see this picture and to see this oil on the left actually has a very low normal level of MPC rating, whereas this oil on the right doesn't look too bad, but has a really high varnish potential. So thank you to our partner in Qatar for this great photo. But this is just something to keep in mind. So MPC test, even though it was developed in the early 2000s for turbine oils, the history of this dates back earlier to that, and the first kind of iterations of this was developed in Japan by Dr. Suzaki, and it's a colorimetric analysis that was done on literally, he did over 10,000 hydraulic samples with using his colorimetric method. So this is something that that is very well suited to hydraulic oil applications as well. Okay, I'm not sure if our poll is working as well as so I will just read this poll out here and read you the answers, and you can think about this. But this is kind of a unique way to think about varnish. So if you have an MPC of 40, we're used to seeing metal spectroscopy, and we see these we'll see, say, 50 ppm of iron in a system. If we had to convert the oil degradation products to ppm, how much do you think we would have? So I think the answers in the poll were, would you have 20 ppm, 200 ppm, 2,000, or 20,000? And so this is just kind of a thought exercise here, but I don't think we've published any details on this, but we've done a lot of testing in our lab on this, and typically an MPC of 40 will represent about 200 ppm of oil degradation products. And that's kind of surprising. It's a pretty low value, I think, and especially because it can create a lot of deposits that you can see throughout your whole system. And but it actually makes up a fairly small amount of material that's actually in the oil. Okay. One thing that I have been questioning recently is that it seems that hydraulic oil users have been absolutely on the cutting edge of understanding particles and isoparticle counts, and however, there's really a lag with compared to, say, the power generation world in measuring oil degradation products. Why is this? So I think it's, in reflecting on this, I think it's a little bit of an issue of the fact that oil degradation products in turbines will cause really, really expensive events. So a trip can be an extremely expensive event for a power plant, which warrants immediate attention and a lot of focus from senior management on what happened with this oil. Why is the unit no longer producing power? Whereas in hydraulic systems, and some systems in particular, that there's so many controls on them that typically oil degradation products and varnish will result in a kind of a slow decay in the system and reduced efficiency over time, but not necessarily big expensive events. And even if you have, in many cases, hydraulic systems are smaller in size. So even if you have a pump fail or a valve fail, which can be somewhat common, but it's still not a super expensive event. And so I think this is one of the reasons I'd like to think of the analogy of frogs that are sitting in hot water and will sit in the hot water until it's boiling and don't really pay attention or notice until it is boiling. And so this is, I think, one of the contributing issues why we see oil degradation not performed as regularly as it should be with hydraulic oil users. So don't be frogs in hot water. Run your MPC test. All right. So the next part I want to talk about is one of the additive components that are very common in many hydraulic oil formulations. So it's a chemistry known as zinc phosphate, or ZDP, and this is a really cool additive that we've been using for decades, and it's fairly inexpensive and provides not only really strong anti-wear protection, but also antioxidant protection. So it's a multifunctional additive chemistry. And since it's in so many different additive or hydraulic oils, I think it's important to understand, how to go about measuring the health of this. So this is a typical oil analysis report that you would see. And in this case, the laboratory did a nice job of breaking out here are the wear metals, here are the various different contaminants, here are the oil additives. And so we have zinc and calcium, phosphorus. Typically, ZDDP will give you, these are probably common levels, 400 ppm of zinc, 250, 300 ppm of phosphorus, and a little bit of calcium. And so a lot of people will just look at this value and say, hey, my hydraulic oil is healthy. Everything looks good. Zinc hasn't changed at all. When in fact, the ZDDP molecule may be completely decomposed and not providing any protection in your system at all, but it's still showing up here as zinc in your system until it actually comes out of the fluid and forms sludge or somehow comes out of the fluid. It's still always going to be measured in the fluid, and again does not necessarily tell you the health of the ZDDP molecule. So how can we best understand this chemistry? I'm not going to go into great detail on this, but this is a cool example that just kind of shows some of the complexities involved with ZDDP chemistries. So this is a test known as P31NMR, a nuclear magnetic resonance spectroscopy. It's similar, actually it's very similar to an MRI. If you ever go to the doctor and you need an MRI, it's a very similar test, but in this case, we are looking at changes in phosphorus compounds. And here is some of the complexity that we see with ZDDP degradation. So this is basically an engine oil application over 6,000 miles. And the first thing that we're looking at is the actual ZDDP molecule. And actually at 2,000 miles, there's no more ZDDP. It's completely been decomposed. However, decomposition products have kind of come in and been formed through this degradation product. And these decomposition products 1 and 2 actually can provide superior anywhere protection compared to the original ZDDP molecule. So even though ZDDP is depleted, it's still providing a strong level of AW performance. And then the next 2 decomposition products are being formed through oxidative reactions. So again, kind of failing through a very different reaction, no longer a anywhere reaction, but more of an oxidative reaction. And then the final product from ZDDP degradation is a phosphate, and then this will kind of gradually form as these decomposition products are reacted out as well. So what a cool tool. Are we going to incorporate P31NMR in our oil analysis program? No, it's I would say this is much more on the research side of things. It's an expensive test, and it is really complex, I think, to understand the chemistry. So the purpose of me just going through this is not to encourage you to incorporate this in your oil analysis program, but just to give you an example that there's a lot of things going on when ZDDP is decomposing. And at the end of the day, you still will have a little bit of zinc and phosphorus and calcium left in the fluid that you're measuring in your oil analysis program. And it doesn't necessarily mean the oil is not healthy. So one of the things you can do that's a little more economical, much more economical, that all labs should be able to run for you is a D7412 at FTIR test, which is looking at the total spectrum of the ZDDP molecule, and this can provide some level of indication of the health of that molecule. The other thing is, because that ZDDP molecule acts as an antioxidant, the ruler test is really good. So the ruler test is not measuring zinc or phosphorus, it's measuring the antioxidant properties of the fluid. And so even if the antioxidants are completely gone, it doesn't necessarily mean the anywhere properties are gone. So that's just something to keep in mind. But if you add these 2 tests together, it really can give you a better insight into the health of your ZDDP molecule. Actually, an insight, whereas I would say elemental spectroscopy does not really reveal too much about the health of your this particular additive chemistry. Okay, a little bit on oil analysis. I think the big takeaway here is fluids are failing. Hydraulic oils fail often due to oxidative stresses and the formation of deposits. You don't want to be blind from this, and ignorance is not bliss, because it will in fact result in operational issues and costs. So it's much cheaper to understand the issue, do the right test at the right time. The next thing I'm going to talk about is different things we can do to control these degradation products in hydraulic fluids. So varnish filtration technologies is something that I would say is somewhat near and dear to my heart, and what FluidTech's been involved in for the last quarter century. We have done a lot of work with media, or with resin medias, to remove soluble contaminants. Depth media is also a technology that we employ, and electrostatic oil cleaning. And so all of these technologies actually work really well if you apply them to the right application at the right time. However, when you start to deal with hydraulic systems that may be a little bit smaller in size, the cost for having a dedicated kidney loop filtration system becomes pretty high. So if you have a 3,000 gallon turbine oil system, or even a 3,000 gallon hydraulic system, the relative cost per cost of the system for the gallon of the oil is somewhat reasonable. However, as you get down into much smaller size systems, it becomes pretty expensive. And I am not aware of anybody with a 100-gallon system and put a kidney loop varnish mitigation system on. And so it becomes somewhat cost prohibitive. So one of the things that we have been spending a lot of time investigating over the last decade is a solubility enhancer. Is there a way that we can increase the solubility of the fluid to allow it basically to hold on to oil degradation products? Having a bunch of oil degradation products actually contained inside the fluid is not necessarily a problem. It's only really a problem once they come out of solution and start to plate in the internals of the system. That is when challenges start to happen. So is there a way that we can actually contain all of this in the system or in the fluid, and not only use solubility enhancer to decontaminate the deposits that have already formed in the system, but also prevent further deposits from happening? Well, before we can answer this, the first thing is, if you do look at a solubility enhancer, it has to be practical. So in other words, it doesn't really make sense to have specialized blending equipment. That is just impractical. You have to be able to add something that's fully miscible, that has a wide range of compatibility, not only with the oil, but also the systems, system compatible materials such as seals and paints. And it has to be really effectively able to solubilize oil degradation products. And so that's the first thing. The second thing is, it has to be safe. So even though this is a pretty simple, scalable solution, if it's not safe or could adversely affect the other performance properties of the fluid or the additive components, then it doesn't make sense. So compatibility is a really, really important property, is essential for this, and also ensuring adding something to the fluid doesn't actually impact, the fluid's ability to interact with contaminants, so like with air or water, and also it can't really have any surface active properties that could potentially interact with corrosion inhibitors or other surface active additive components, anywhere or EP agents. And then the final thing is, you don't want to add something to the oil that will oxidize and long term actually start to create additional varnish. So if you want to add something to the in-surface oil, you want to be able to basically add something that is not going to contribute to deposit problems. So we've developed a technology that we refer to as Solvencer, solubility enhancer. You can probably see how we came up with that name. And this technology and various iterations we use in different products. In the world of hydraulics, we have a technology that referred to as decon, and it's a chemical solution. We refer to this as a chemical solution for varnish, and it's really simple. So it's you can add this at a treat rate between 3 to 5% into the in-service operating fluid, and it has a wide range of compatibilities from group 1 to group 4 fluids. From an additive point of view, we would say there's no issue with antioxidants, with EP or AW agents. However, we probably would not put this into a detergent dispersant-based system. So in that particular, like engine oils, we would not add this to engine oil type applications. So, and again, this is working by increasing the solubility of the fluid and dissolving oil degradation products. So how can, if you're increasing the solubility of the fluid, well, there are some soluble and some maybe not so soluble or insoluble components in the fluid, especially in hydraulic applications. We just showed the final degradation product of DDP as a phosphate. Phosphates are not so soluble in in-service oils and may actually come out of solution and form an inorganic or a insoluble deposit. And so this is an image of a microscopic image of varnish, and all these little dimples that you're seeing here, basically hard contaminants that are stuck to this. So we like to use the analogy, it's like sandpaper. The insoluble components are being stuck, it's like the sand that's being stuck to the glue, which is the soluble components that are, and that is a varnish. So if you add decon, you're not going to dissolve, say, dirt in the system. However, you will dissolve the varnish. It's kind of holding the dirt onto the system, and then that is able to be released and captured with normal inline filters. The other thing is, how does this work long term? And so also, how quickly does this increase solubility? How quickly does this get filled up? So we do know that, varnish itself actually makes up a fairly small percentage of the oil. 200-ish ppm. We could see higher levels than that, but a relatively small amount. But it's important to see how this works, long term. So this is an example of a new oil that we beat up in a really accelerated oxidation test that basically stresses the oil at 120 degrees for about 6 weeks, and the fluid, essentially our goal, 120 degrees C with catalyst and air bubbling through it. We want to try to kill the oil. So new oil in this particular case, we saw the antioxidants have depleted, and we see a fairly high varnish level. You add the solvents or technology to the new oil, run the same test again. It's not impacting how your antioxidants are depleting. It's not impacting the oxidative stability of the fluid or the acid number, but oh my goodness, it has a very significant impact on the formation of deposits. And we have correlated this particular test to in-service fluids, and this equates to about a year of 1 week would be about a year of service in a large frame gas turbine, which is already a pretty stressful event. So this is maybe looking at 6 years in a especially stressful, say in this case, a large frame gas turbine. Hydraulic oils are not going to last as long. So typically hydraulic oils, after 2 to 3 weeks, you're going to see a much higher level of degradation. But what happens if you run this out for a really long period of time? This is just a visual example here, the glassware and the deposits. But if you run this out for a really long period of time, here we have a solvent that's been added to this fluid that after 18 weeks, so 3 times longer than when most oils are failing, we still have single-digit MPC values. And interestingly, the antioxidants were depleted in this range here. So even after the antioxidants have been consumed, it's still allowed or prevented the oil from forming deposits. So it has a pretty phenomenal ability to hold a lot of contaminants for a fairly long period of time. So a couple just quick case studies I want to share with you. The first one is a hydraulic forging press, fairly large system with 4 separate 12,000 gallon reservoirs. And they were noticing a decrease in ram speed and somewhat inconsistent performance. So They also noticed deposits throughout the system. And so based on oil analysis, we saw a fairly high level of varnish, as one would expect in this application. After, in this case, we added 3% decon, and within a week, actually very quickly, we saw the varnish potential drop, and some of these components that were before really heavily coated with varnish actually started to clean up a lot. So this is just a little trend of the MPC. Actually, this was in a week, the MPC dropped down, and then has actually been maintained at a low level here as well. So we saw that, this is a fairly simple thing to add, and it did result not only in a rapid decrease in MPC. Quite honestly, the customer in this case, I would say, did not care so much about the MPC value. They were much more concerned about the consistent performance and the RAM speed. But that is something that we saw that improved. So that was a good case study. And one more I want to share with you from a plastic injection molding machine. This was a large manufacturer of consumer products. This is a Millicron 1,000-ton extruder used for manufacturing, and they also found deposits throughout the internals of the system. Some of the operational challenges they saw, this is a heat exchanger that actually was not operating. And as a result, the oil was running at a fairly high temperature. So the absolute maximum that this oil can run at is 140 F, and it was fluctuating between 135 and 140. And so the oil's running at a very hot temperature. And also each morning, when you start the machine up, everything is sticking. And so it takes much longer to start the machine up. Servo valves were sticking, and so that was also a challenge. So we added some decon. If you get decon, there's our decon delivery boy. I'm just kidding if Darren's watching. He's one of our sales managers. So we added, in this case, a 5% treat rate. Couple hours later, actually, we saw the MPC drop from 40 to about 10. So that was good. But longer term, within a day, the heat exchanger started working. It hadn't been working for ages. The heat exchanger started working, and we actually saw the oil temperature drop down to 95 degrees. So just based on the Arrhenius rate equation, which basically states every 18 degrees F or 10 degrees C increase in temperature, that will double the reaction rate or double the rate of oxidation. So reversely, if you're looking at this in the reverse, we are lowering the temperature by 40 degrees, this is actually looking at maybe a 4x. Immediately, we're going to expect a 4x impact on the life of the oil and significantly less thermal stress. So that is good. The other thing is now their mornings are a little more chill. They turn the machine on, things start working, valves start operating. There's no hammering of valves to try to get everything moving. So that has also been helpful. And also the mold clamp speed has increased, and this can directly be tied to product yield. And if you have a higher product yield per machine, you can directly tie that to profitability and how many products are going out the door. So it's actually a pretty quantifiable value in increasing the efficiency of this machine. So to conclude, oil breakdown and varnish formation is a common form of oil breakdown in hydraulic fluids. There are a wide range of different mechanisms that can be at play, but the bottom line is, if you are not actually measuring hydraulic oil for the formation of varnish and deposits, you just may not be aware of all of the performance impacts that are happening. So please run MPC test or another test that is looking for the varnish potential of the fluid. And the second thing is, one potential solution to this is using a solvencer technology or a solubility enhancing technology. It's a safe way to not only decontaminate the lube oil system, but also protect the fluid from producing further varnish. So thank you very much, and I'll just pause here to see if Greg's found if anyone's asked some questions here along the way.
Yeah. Hey, Mike asked a good question here just a minute ago. Actually, we have a couple of good questions, but he asked when you were speaking about solvents, what is the maximum temperature it can be used in the system?
Okay, good question. So it's the flashpoint and volatility of this technology is similar to a Group 1 base stock. So you can operate this up to 200 degrees F without a problem, but once you start to get above 200 degrees C, then you're starting to get close to the point where some of these components are going to be volatile. So, but certainly up to 200 degrees F. So I can't quickly, maybe 75 degrees C. I can't quickly do that conversion in my head, but 200 degrees F is a safe maximum limit for a solvencer.
Also, I think this is more of a question. I mean, more of a statement than a question. But it said they had mentioned also poor filtration or not prioritized filtration is an oil an issue in oil, which is just more of a comment than anything. And then another question came about Firequill. Will we be talking about Firequill? Maybe not in this session, but that's definitely something that we can add to our webinar list.
Yeah. So, okay. So the first point is that filtration is always something that I think can be looked at and improved on. And the comment is absolutely right. In most cases, people are not using adequate filtration, and there's great opportunities. That can be maybe the biggest bang for the buck you can get in your lube oil program is to assess your filtration systems. So that is absolutely a very valid comment. In the world of hydraulics, however, I would say that, hydraulic oils are really, and hydraulic oil users have really been on the forefront of understanding hard contaminants and the importance of running isoparticle counts. And so there are some hydraulic oil users that are somewhat advanced in understanding the criticality of maintaining low particle counts. And maybe I should have clarified at the beginning here. There are so many different hydraulic fluids out there. There are a wide range of Group 5 hydraulic fluids, polyol esters, phosphate esters. There's invert emulsions and fully emulsified, 95% water, 5% oil type solutions that are used. There's detergent-based. There's sometimes people are using engine oils for hydraulic oils. And yeah, the comment is absolutely right. We really only had the opportunity to talk about basically traditional mineral oil, hydraulic oils used in industrial applications. But future webinar, we will be talking about phosphate ester management as well.
And then the last question, then this may be a two parts, kind of hard to understand. What tests do you conduct on new and used fluid?
All right. So on new fluids, there's a wide range of different tests that people will do. OEMs may require in terms of qualifying a new oil for use in a particular application, which you may not run, say, for an oil condition monitoring program. So one example is the turbine oil stability test, ASTM D943. In some cases, it tests some fluids they may fail after a couple thousand hours. Some fluids, the maximum limit on the test is 10,000 hours. Clearly, this is not a suitable test to do for a condition monitoring program. So there are some unique tests that are required for new oils that OEMs will require to make sure that the fluid has sufficient oxidative stability and will be able to perform long term. But for in-service fluids, the most important thing is understanding what is a mode of failure for that fluid in this particular application, and then what oil analysis tests are you going to be running to be able to measure that mode of failure. And in the world of hydraulic oils, measuring contaminants, so isoparticle count and elemental spectroscopy is really important for understanding where metals and other foreign contaminants may ingress into the fluid. water. Certainly, water by Carl Fisher is a good test. Understanding what tests will interact with what tests will illustrate if the fluid can interact with contaminants. We would look at ASTM-D 892, the foam test, to see how it interacts with air, or the air release test as well. And also 1401 is a demulsibility test, so we would recommend that. Chemical changes, I think this is in particular if you inadvertently add a different chemistry to the fluid. FTIR is a great tool and fairly inexpensive to run for this. And then oil degradation, I talk specifically about the membrane patch colorimetry test, but there are other tests as well. Ultracentrifuge can be used. There's a variety of other, you could use a gravimetric patch test, but since all oils are going to be susceptible to contaminant ingression, we need to be monitoring contaminants. And since all oils are going to be changing molecularly or forming deposits, these are also tests that are really important to run for in-service fluids.
Hey, Greg, we've just got inundated by a lot of really good questions, so let me run through a few of these. After adding Decon, do we have any special filtration systems to remove the dissolved varnish?
Yeah, so there are filtration systems. So our ESP technology does a really good job of removing these solubilized degradation products. However, the degradation products they're not really causing any issues when they're actually solubilized in the oil. And if they're not coming out the MPC test, they're not going to be coming out and plating out in the internals of the system. And so in many cases, it just, as long as you are able to solubilize these degradation products for a long period of time, then you don't need to add a filtration system on as well. And also, I would say that this is not just a magic elixir that suddenly solves all problems. You don't have to worry about oil analysis. Still run MPC tests. You should expect to see single-digit MPC tests for a long period of time. But the fluid is still oxidizing. It's not actually stopping any of these degradation mechanisms. And so ultimately, we want to, at some point, the solubility enhancer may have a limited ability, and then we will start to see the MPC slowly start to increase again. So I would say, even if you add Decon to the system, you can monitor the performance of this long-term by continuing to run the MPC test.
All right, next question. Solver, is it okay to run solvents in a system continuously, or should work limit period, or should be limited?
So we have different kind of chemistries of solvents. So we have one product that we call Boost VR. The VR stands for varnish removal. This is designed for short-term application, so say for up to 6 months. In this particular case, the solvencer chemistry is a little bit more active. However, it doesn't have the same life expectancy that say Decon would have. Even though it's the same kind of chemistry, if we can still alter the chemistry of it by looking at the molecular chain length. So we would use a more stable product for Decon that will last for the life of the system. In the case of Boost VR, that's also using solvencer, we would say maximum of 6 months in an operating system.
Okay. If Decon is added to a heavily contaminated system, it helps lower the varnish deposits. Once we finally end up changing oil, it's typically best to do this while warm, hot to avoid redepositing the varnish particles. Is this true with Decon? Also, in this scenario, should Decon be added to the new oil?
Okay, good question. So yes, it's also true. Basically, what we're doing. There's two things you can do to impact the solubility. The big thing you can do is temperature. So the warmer the oil, the higher the amount of solubility. So very very good comment. When you are draining your in-service oils, drain your fluids as close to your outage as possible while the fluid is still ideally warm and everything is still in solution, rather than after everything's cooled down and settled out in the system. Same thing when solvencer is added to it. Solvencer will in fact work more if there's a little more kinetic energy in the fluid and molecules are flying around a little bit faster. And so at higher temperatures, we're going to see quicker results than at cooler temperatures. So same principle applies when changing the oil. And I'm sorry, Greg, what was the second part of that? Can solvencer be added as well to new oils?
New oil, yes.
Yeah, so decon is something that is commonly added to new oils. We would not necessarily endorse buying really cheap hydraulic oils. But we have seen some plants that buy very, very inexpensive oils that can fail fairly rapidly, but at least adding decon to it will prevent the fluid from developing deposits. It still may fail due to anywhere additive depletion or other properties, but at least in terms of deposit control, adding decon to new oil is going to enhance the ability of that fluid as well.
Okay. Do we need to check viscosity after adding decon?
Yeah, it's a very, very good point. In light of the fact that viscosity, what we say is the most important, the first and the second and the third most important properties of fluid. So you should absolutely check for viscosity. And again, we also have different types of decon that we can add to lighter or lower viscosity fluids or higher viscosity fluids. Good question.
All right. In which frequency is appropriate to use solvencer?
I'm sorry, say that again. In what?
I think how frequent is it appropriate to use solvencer? I think
so. Okay, so I think you can think of solvencer maybe like adding a little bit of metal to metallurgy. If you add a little bit of chromium to steel, you're going to greatly change the properties of that metallurgy. And it's similar to adding decon to an in-service oil. You add a little bit to it, and you're fundamentally changing the solubility of that chemistry. There's no property that is depleting in decon. There's no need to add more to the fluid over time. However, especially in hydraulic systems, there's often leakage and top-ups. And so it's important maybe to monitor the concentration of decon in the in-service oil and ensure that you maintain a consistent level of decon. So if you add another 20% new oil, you top up the system with 20% new oil, you may also want to put a small amount of decon back into the system as well to kind of rebalance that.
All right. Next one. For how long will 4 to 5% of decon control MPC?
That's a really good question and a very challenging one to answer, I would say. But in every application is different because a generation of degradation products is different it's all based on application. But in this particular case where we add this to a decon to in this particular case to a turbine oil that then we beat up with a ton of thermal pressure for a really, really, really long period of time. In fact, we're not showing this here, but we've run this for much longer than 18 weeks as well. And we are still seeing single digit MPC values. So we would expect this to last for a very long time in an oxidative environment. But trying to quantify that more based on, then it really comes down to a specific application.
Yeah. Hey, Greg, there's probably 25 other questions, and they're all really good questions, and there's no way we're going to get through these. And we wanted to cut it off at an hour. But we know who asked these questions, so we can get back with each of you on all of them, unless you want to take one or two more.
I think we should respect our time limitations here, and I think I'm very grateful for everyone to stay on here for as long as you have. So,
hey,
yeah.
One other comment that was made, I had several people ask, will this presentation be available and the recording? And yes to both. We'll send out the presentation and the recorded version of this to everyone that was in attendance.
Great. That's excellent. Okay. Good. Excellent. Well, on behalf of FluidTech, thank you very much for joining. And I am sorry that I don't get to see you, but hello and thank you. And hopefully we will whatever we can do to help answer further questions you have. Please let us know. This is something that we are deeply passionate about. We love understanding oil degradation and all the different nuances of this. So reach out to us and please let us know how we can be of assistance.
All right, everybody, stay safe.
Thank you. All right. Bye-bye.